Okay, so welcome. This is lecture 16, and today we're talking about contextuality in measurement-based quantum computation. So we are in the middle of the MBQC discussion. So two weeks ago, we talked about universality, and then last week about fault tolerance. And so kind of the main subjects, I mean, everything that really needs to be talked about is talked about, and now we come more into these structural things. And there's going to be two of them, and contextuality is the first. Okay, so this is about putting a contradiction to work. We are familiar by now with the Cauchy-Specker type contradictions. We saw them in quantum computation with magic states. So this is the outline for today. So I will begin with a recap of non-contextual hidden variable models. I mean, we saw this, but just to make sure. And I want to formalize the MBQ setting a little bit. And then we do the contextuality discussion in two steps. So we look at an example. This example brought about the whole discussion. It's a paper by Janet Anders and Dan Brown. So we will look at that, and Mermin star will play an important role in it. And you know Mermin star by now, and I think it appeared in the homework assignments. And so a lot of what you did in that particular homework assignment will be important for today. Okay, but that is the MBQC contextuality connection in a specific example. And after we are done with the example, we want to look at it in the general case. So that's the plan for today. Okay, so there is some reading that you might pursue. It's about these two items. It's about the Mermin star repurposed, taking Mermin star and converting it into a measurement-based quantum computation. So this is the Anders and Brown paper that I already mentioned. And then about the general case. So there is a paper from my group, and then there is a follow-up. If the theorem in here is not general enough, then you can look at the Abramsky and company paper. They make a further generalization of this. Good, so this setting, hidden variable models. So this was the situation, quantum mechanics. In quantum mechanics, you have a quantum state. That information or that thing here contains all you could possibly measure about a certain physical scenario. Everything comes from that. And now the hidden variable model is a proposed alternative description of physics. And so you think of this as a particle or whatever, and it has a catalog attached to it, pretty much like you would see it here, but we come to the differences in a moment, that tells you when I measure a certain quantity on that state, the system, output this outcome. And it has this catalog for everything you could potentially measure on that system. So it would be a very long catalog, but we are not really concerned here with practicalities. Yeah? So it's just that you have this. So what singles out this model is that observable quantities have predetermined values since the beginning of time. Yeah. Okay, so now measurement in quantum mechanics is random, so you want to model the randomness with a particular type of particle having the possibility of different such catalogs attached. So in one catalog, the values may be, say, +1, -1, -1. In another catalog, they are all -1. So catalogs can differ, and they can be distributed according to some probability distribution. So that's the idea of mimicking the randomness of quantum mechanics. And now you want to see if this checks out. Yeah. And so the way we have written here is kind of suggestive. The values that are assigned only depend on the observable potentially measured, only on the observable. And that is a non-trivial assumption. That's called non-contextuality. So if multiple observables are measured, so say that the first observable A is compatible with two other observables B and C, regardless of whether B is compatible with C or not, just these compatibilities we need. So if we have them, then it doesn't matter for the value of A if A is measured with B or with C. That's the assumption of non-contextuality. The measurement outcome for A does not depend on the measurement context. Okay, so that looks kind of almost not worth mentioning, but it is not so innocent. So if you assume this assumption, then you have a theorem that these models don't work. And that's the theorem of quotient in Specker. And it holds in Hilbert space dimension 3 or greater. Okay, so in Hilbert space dimension 3 or greater, these non-contextual hidden variable models cannot reproduce the predictions of quantum mechanics. And we have seen a simple proof, slightly weaker than the quotient Specker result in dimension 4 and up, and that was Mermin's square. And then there's this other thing, Mermin's star, it's in dimension 8, that you have seen in the homework assignment, and Mermin's star will be very important today. Okay, so that was just a recap of contextuality in quantum mechanics. Oh, I haven't explained what that is. So we say that when we say that quantum mechanics is contextual, this is just a kind of a shorthand for saying that quantum mechanics does not admit non-contextual hidden variable models. Good, so much for that. And now for the purpose of today's lecture, we want to formalize measurement-based quantum computation in a certain way. So there's certain assumptions that we want to make explicit. We want to remember what the various parts are. So in measurement-based quantum computation, we have a classical control computer, and that thing determines the adaptive measurement bases and collects the measurement outcomes and outputs certain functions, certain correlations of the measurement results as the computational output, and it also takes an input. I mean, we maybe want to evaluate a function or something. Okay, so input is classical, output is classical, the middle is quantum, but it is controlled by some classical site computation. And that is the part that we actually want to formalize. And we know what that site processing is, but we want to review it here. I mean, we saw a little bit of this in the universality. Okay, and so just kind of to give us an opportunity to review this, we asked two questions. So first question, the local measurement outcomes are all random. And so does this mean that the resulting computation is probabilistic? First question, the measured observables all commute. And does this mean that the resulting computation has no temporal order? Okay, so what is your opinion on this? So this was part of the universality proof. So what comes to mind when you see these questions? First, yes. Second, no. Which position do you want to defend? First or second? You can choose.
Let it be second.
Second. The measured observables all commute. Has the resulting computation no temporal order? You said second, no. Why?
Since we have, I assume, some kind of time evolution.
You have some time, yeah.
Observables do not depend on each other in terms of which order do we apply. I mean, not influencing each other, but it depends at which moment of time will we measure them.
Yeah, and look, if the measurements all commute, why don't we measure them all simultaneously? Okay. Good. So let's review this a little bit. I mean, these two questions, they are closely linked. Yeah. So this is in an example. So we have a 3-qubit cluster state here, and we measure 3 times. 3. Yeah. So it's just. I mean, you've seen all this in the universality proof. I think this was 2 lectures before this one. Yeah. So I'm just recapping it. So what this does, it simulates this circuit. So we have a preparation of an eigenstate of sigma x, then we have a rotation about the z-axis, about some angle, then we have an x rotation about some other angle, and then we have a z rotation about a third angle, and then comes an x measurement. So this is what this MBQC does, but not exactly. So what it does is here in the end, you really rather have a projection onto plus, but maybe that's a minor detail. And then you have these, what we call byproducts, this random stuff. So the stuff that is controlled by the measurement outcomes. Yeah? So here we have an outcome, depending on what it is, eigenvalue plus or minus 1, you have an additional Pauli Z here or not. You can't choose what you have, but you learn afterwards. Yeah? So this thing is there when the eigenvalue measured was negative, was minus 1. Likewise here, you want to implement this X rotation, but you get this thing in addition or not, depending on the outcome of the second qubit. Now you get a third Pauli Z, regardless of whether you want it or not, depending on the outcome of the third measurement. Yeah, so we remember that. This was part of the universality proof. Okay, so we don't want these pieces, but we have them. So we need to get rid of them. And the idea of getting rid of them is just propagate them past the readout measurement. Yeah, whatever happens after the final measurement cannot be of any concern to the computation. So we propagate them out. But on this path, they kind of wreak havoc a little bit. Yeah? So when we're propagating this thing forward in time, it is flipping these angles because of the ZX anti-commutation. Yeah? So the angles are being flipped here, and you need to take note of that. And furthermore, it also flips the outcome of this final measurement because of the ZX anti-commutation. So the measurement outcome is flipped, and these angles need to be adjusted. And so we find the computational output is the sum of those. I mean, this is now in binary notation, 0 and 1, rather than plus 1 and minus 1. So the output is flipped, is given by the sum of these two outcomes. Yeah? Qubit number 1, qubit number 3. Both of these affect the readout. And then furthermore, bases, we have adapted basis choices. So this guy influenced the basis over here. So we see this right here. And the second measurement influences the choice of the third measurement basis by precisely the same effect, same anti-commutation relation. Okay, so let's remember that. So we have a classical output related to measurement outcomes. It's just a parity. And then we have further linear relation for the adjustment of measurement basis according to measurement outcomes. So these are all mod 2 linear relations. We see it here in an example, but this is actually the general situation. Okay, and so now with this, we can go and answer those questions. First question was, just an observation to begin with. The local measurement outcomes are all random. Does this mean that the resulting computation is probabilistic? It carries all this randomness in it. And so that is not the case. What the output is going to be in the end is parity of measurement outcomes, not individual measurement outcomes, but certain parities of them. So certain measurement outcomes are added up. Yeah? So output is given by correlation, hence the title in the Anders and Brown paper. So let me go back. Yeah, so this is your reading suggestions again. Yeah, first paper to read is by Anders and Brown, the computational power of correlations. So that is what it refers to. And we'll see this in some detail. Yeah, okay, so the outcome, so while each of these measurement outcomes that occur here are individually completely random, 50-50, the output need not be. Okay, second question. The measured observables all commute. That's true, it's just an observation. And the question is, you think, okay, if something commutes, you can measure it all at the same time. And the question then is, has the resulting computation no temporal order? No, it's not exactly the case here in our setting, because even though the observables we measure commute, the choice of the observables we measure depends on the results of earlier measurements. So this is the second relation we saw on that previous slide. We have these relations. And they mean that in order to find the choice of measurement basis at some qubit k, we must measure qubits at other locations first so that we can figure out what the measurement basis is going to be. So there is temporal order even though the observables commute. All right, and so all these questions, this was just to motivate the following definition. So this is this notion here of L2 MBQC. L2 stands for linear mod 2. Okay, and so just before we go through the details, what this definition concerns is not what resource states we deal with and so on and so forth, like cluster states or other states. It doesn't talk about that, but it specifies the classical site processing of this type of measurement-based quantum computation. And this is just a formalization of what we have in the cluster state case or related cases anyway. So it's not a particular absurd definition, but we just kind of collect the features that we saw. And the results that we find out about the connection between MBQC and contextuality will refer to that more. Okay, so that's why we have this definition now. So what is in it? So first thing, binary choice for each local measurement. So there's two choices of bases and they are flipped from one to the other depending on what the measurement outcomes are. But I'm getting ahead of myself. So first there is a binary choice for each local measurement basis. It's the first thing. Second thing is that the measurement outcomes are two valued. So we're not talking about Hilbert space dimension or anything, but the measurements that we do, they are supposed to have only two outcomes, and we may call them 0 and 1. That's exactly as we saw in the case of cluster states. So now comes the classical processing. So first is the relation between computational output, bitwise, bunch of bits may come out of this, and measurement outcomes. Computational output, individual measurement outcomes. So what you see here, so this is a matrix. So bitwise, the output is a parity of certain measurement. And all this is mod 2. So that's exactly how it was in the cluster state case. Likewise, we have a relation between the choice of measurement basis. So binary choice. First item, binary choice of measurement basis, like so or so. And that depends on previous measurement outcomes, exactly in the way we have seen, linear relation, mod 2. But then also what comes in here is the input. So imagine you want to evaluate some Boolean function, which is what we will talk about. Boolean function takes a bunch of input bits and maybe computes a bunch or a single output bit. And that is the computational input over here. And we add that bit. So this is the way in which input is supposed to enter into the computation. Okay, and then, so this is a point here. That matrix is supposed to be compatible with temporal order. So we've seen before, this part of the relation governs the temporal order. And so basically this lower triangular property, what it does is it avoids closed time-like curves where A influences B and B influences A. So we are finding a suitable basis where earlier qubits measured earlier have a label higher up and qubits measured later are further down. And then you get this lower triangular form for this influence matrix. So this lower triangular form with the right labeling is just a reflection that this matrix is compatible with a partial order of measurements. Good. Okay. So we are soon done with the formalities. Soon we will look into this example. Okay, but there is one One thing I would like to clarify, how we apply kind of a non-contextuality setting in our MBQC scenario. And the reason there's something to talk about, I mean, the Greenberger-Horn-Zeilinger state in the Merman star example, this is, so where it sits in this whole fields of contextuality is where contextuality and non-locality meet. Yeah? And so when you're thinking about non-locality, then in such scenarios, you are forbidden to have communication between parties. But in measurement-based quantum computation, communication is essential. Yeah? So the measurement outcome of some side needs to be communicated to the other side so that the bases can be adjusted. Okay, so that's why we need to be a little bit careful about what's going on here. So why can we have communication in our scenario? And so now here we defined the scenario. So this is the time axis running from left to right. So basically beginning of time somewhere over here. Yeah, and so then some quantum state is prepared at some beginning. And from the hidden variable model perspective, we say that a value assignment is fixed. So from this variety of catalogs, dice are rolled and one particular catalog is picked. And at that point, all the value assignments are fixed. Then at a later, so that is kind of the alleged representation of the quantum state. And so at a later time, the input to the computation is chosen. So suppose we want to use the quantum computer to compute a Boolean function, and we want to figure out for which input value that function is evaluated. So that is when the computation happens. So the HVM state preparation is at the beginning of time. Then for a long while nothing happens. Then the input is chosen, and then the measurement sequence begins and eventually leads the computational output. So that is the setting that we refer to. Yeah, so this is supposed to connect the hidden variable model idea in measurement-based quantum computation. Okay, so that was the preparation, and we can now begin to figure out what we can say about such scenarios. Again, questions? Yeah, on up.
Yes, can you explain a little bit about what it means to choose the input, like for a 1D class tested?
Yeah.
Encode I into the initial qubit, or?
Oh yeah, so that's so suppose you want to, I mean, what does it mean? So suppose you want to factor some number. Fixing the input means choosing the number that you want to factor. Yeah, something like this. Yeah. Or I don't know, you want to compute some fixed Boolean function, say a bend function. We'll come to what that is later. Yeah, and you want to evaluate that function at a certain input, and you have to choose it. So that's what it means. And now, how that input enters into the computation. And it enters like this. So it doesn't have anything to do with the resource preparation. It enters through the choice of measurement bases. Okay, and we will see an example for that, yeah, next. Here's the paper that we are now looking at, computational power of correlations. So that is the example. I mean, the famous example, and it has to do with Merman's proof of the Cauchy-Specker theorem. So that's precisely, I mean, Merman had already proposed the square, which, going from the original result by Cauchy and Specker, I mean, goes up from dimension 3 to 4, making it slightly weaker. But the advantage of this thing was, I mean, Specker's result really Cauchy-Specker's result really requires some patience to verify, whereas Merman's square, not really. Yeah, it's an elementary calculation. Yeah, but Merman wanted this connection between contextuality and locality, and that's why he went from dimension 4 to dimension 8. And that's the thing. So I think you've seen it, probably talked about it in the lecture, but you also saw it in the homework assignments. So this is the star, and it consists of something on the order of 10 observables arranged in 5 contexts. So you have 4 observables in each context, and each observable is in 2 contexts. Yeah. Furthermore, well, context means that everything that's in it is commuting, can be simultaneously measured. And so that's what's necessarily needed. But then here in this arrangement, these observables fulfill a further constraint. And that is they multiply to the identity or sometimes minus the identity. You have minus the identity once, and as you probably remember, and it's completely the same like in Merman's square, this minus 1 will then give you the contradiction if you assume values for the observable. So I hope you remember that proof. We've definitely talked to you about Merman's square, and this is exactly the same. So, but yeah, so that's not yet what Merman wanted. I mean, this is kind of an intermediate step in what he wanted, but he wanted a local version with local observables here. And so look, some observables in the star are local, but others are not local. And so he said, okay, let's have this state-dependent version. So we take one context and assign a quantum state to it. And so the assigned quantum state is simply a state that is the eigenstate of all these observables. So that is the Greenberger-Horn-Zeilinger state. And when we do that, then these observables do have values. So you can easily check this. This observable will have value 1. This observable will have -1, value -1, -1, -1. Okay, and so now the contextuality question is, can the local observables be assigned values, yes or no? And the answer is still no. I mean, we're just making it harder to find value assignments, and even when these values were not fixed, there is none. Okay, so we will not have one here. All right, but now the question of values is for local observables only, and that's what Merman wanted. So that is the state-dependent Merman star. It is a contextuality proof that stands somewhere between Cauchy-Specker's original proof and the Bell inequalities, and that's exactly what he wanted. Good. So I'm not reviewing how this proof goes. It's the parity argument. Yeah. So okay. Do you remember the parity argument for Merman's square? Do you think you hear the word Merman square for the first time? No. Good. That's good. So let me just maybe then, if you don't have it present in your mind right now, so let me maybe review the argument here. Okay. So the observables multiply to minus the identity. So if we have values, then these values must respect the properties of quantum mechanics. So quantum mechanics says this is a Pauli observable, so the eigenvalues are plus minus 1. Yeah. So this is what we expect, and so the values lambda, they must be plus minus 1. They must reproduce this. So if we would measure, since the observables commute and multiply to minus the identity, the values would multiply to minus 1. So those hidden variable model assignments have to do that too, have to multiply to minus 1 in this row. And everywhere else where the product of observables is plus the identity, the corresponding values here have to multiply to plus 1. Okay, and so now what I'm now interested in the proof is the value so the product, excuse me, the product of the values in all these 5 contexts. So I multiply everything together. And I can do this in 2 ways. First way is I realize, oh, these values are already pre-multiplied. Yeah? So I can just read off right here what the products are in each context. So let's do that. So we have -1 and then +1 everywhere else. So this is -1 overall. Okay? But then there's a second way to figure out what this product is. Namely, I can observe that every value is part of exactly 2 contexts. So it will appear in this product twice. And so now, individually, every such thing, without knowing whether it's +1 or -1, its square will always be +1. So it's a part of +1s. The whole thing is +1, and so that's the contradiction. Under the assumption that this value assignment exists, one way of figuring out what this product is leads to value +1, and the other way of evaluating this product leads to value -1. So that's inconsistent, and therefore the assumption that the hidden variable model assignment exists must be wrong. So that's the Merman's proof for the star. So now, and this is now what Anders and Brown did. They took this thing and converted it into a little measurement-based quantum computer. So I mean, so what it does in the end is not very impressive. What can you expect from 3 qubits? So what it does, it computes an OR gate. Yeah, so that doesn't sound super fancy. Every dishwasher probably computes billions of OR gates every second. But it is interesting from a computational point of view. So this is not a practically relevant computation. It's just a fundamental point of view. And the fundamental point that's made here is that the classical side processing we had, remember these relations like so, yeah, adjusting measurement bases to input. Yeah, so these are linear. These are linear relations. So, but the OR gate is a nonlinear Boolean function. So this is what happens. So access to this quantum resource, this Greenberger-Horn-Zeilinger state, promotes a classical control computer that can only evaluate linear functions to computing nonlinear Boolean functions. And so you go from some device that is super limited to something that's classically universal. So that's a step up. It's not really the step up that you want in quantum computation, but it's a fundamental point of view. So this context that we still have to show that computing the OR gate is precisely the consequence of Merman's contradiction. But here you see that in this example that contextuality helps you with quantum computation. So I think we want to try to understand a little bit how this works. So what do we see here? So let's maybe begin with Merman's star. So we have 5 contexts here. One is for the resource state. Yeah. So then we have 4 remaining contexts, and incidentally we have 4 input values. Yeah? So we have 2 bits of input for the OR gate. It makes 4 input combinations, 0, 0, 0, 1, 1, 0, 1, 1. Yeah, and each of these input combinations we now assign to one of the remaining contexts. Yeah? For contexts remaining, for input combinations. Yeah, so we do it like this, and how there's simplicity in the assignment, let's not talk about this right now. Yeah, so for example, input 0, 0 is associated with this context over here. So we look at what we have in this context. We have x1, x2, and x3. Good, so when our input is 0, 0, the measurement bases will have to work out to 0, 0, to x, 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 on all qubits. Good, and so yeah, so the following classical site processing relations for input versus choice of measurement basis make that. So for the first qubit, the choice of measurement basis is simply the input bit 1. So if that input bit is 0, then the measurement is in the x basis, and if that input bit is 1, then the measurement is in the y basis. Okay, so for qubit number 2, the same is triggered by the second bit of input that we have for our OR gate. And for the third qubit, the choice of measurement base is triggered by the sum modulo 2 of these two bits of input. So that's what's happening. And yeah, so now maybe let's go through the various choices of input and see what this leads to. Maybe I'm doing 2 rather than 4 so that I can get through this in finite time. So let's say input is 0, 0. So now I'm looking at these relations here. So this means Q1 is 0, Q2 is 0, Q3 is 0. So this means X, yeah, X1 is measured, X2 is measured, X3 is measured. So this means we are in this context here. Yeah? All right, and so now let's see. So now we measure these observables. We measure X1, we measure X2, we measure X3, and individually these outcomes are random, but we know what the product is going to be. So the product is going to be, of these eigenvalues, is going to be +1, because because this value times this value times this value is the value of that non-local observable x1, x2, x3, and because we are dealing with the Greenberger-Horn-Zeilinger state, that value is 1. So no matter what we individually measure, so when we look at the output, the output of the computation is the sum of the 3 measurement outcomes. So here now, not eigenvalues, but the binary values 0 and 1. Okay, so if we add that up, we know that the output of input 0, 0 is going to be 0, corresponding to eigenvalue +1. Yeah, or value lambda equals +1 over there. Good. Is this clear? So I will do one more example, and I'll maybe choose Q1 equals Q2 equals 1. If you like that. But before we go through that, is it clear what I did here? What the reasoning was, or maybe not? So I think this would be a good moment to ask.
Output of 0 direct.
From what? Okay, so maybe something I should have said, because I'm switching here between additive and multiplicative notation. So maybe that is something I should say, that lambda, the eigenvalue, is -1 to the power s. So when so s is a binary variable in 0 and 1, and the eigenvalue is +1 or -1. Yeah, so maybe that was confusing. So the lambdas multiply, and the corresponding values s add up modulo 2. That's the correspondence. Yeah, and so when I'm writing this sum modulo 2 up here, this corresponds to multiplying the corresponding eigenvalues. Yeah, and so here measured eigenvalues ±1. I don't know which one. Here same. Here the same. But since the product of these 3 observables is that observable, and that observable has a definite eigenvalue, namely +1, the product of these eigenvalues will multiply to that value, or expressed in terms of the s's rather than the eigenvalues. The sum of these s's for this x, and that x, the sum of these s values, they will add modulo 2 to the corresponding value s over here, which is 0. Yeah? So that is, individually they are random, but when I look at the correlation, I will have this outcome with certainty. Yeah? So this outcome, 0, corresponds to eigenvalue plus 1 over here. Just for good measure, let me, for good measure, let's just do another case. Or do you, anybody interested in a particular one of the remaining cases? Okay, then let me do the case of 1, 1. Okay, so I'm looking at these relations again, so I find, so you tell me, Q1 is?
1.
Yes. Q2 is the same, and Q3 is what? 0. Yeah. Okay, so this means Y1 is measured, Y2 is measured, that's not very nicely written here, Y2 is measured, and X3 is measured. So now I'm, according to my earlier drawing, it is this context. And now let's see if this is true. Let's see, we are supposed to have Y1. Yeah, Y1 is right here. Y2, yes, and X3. Okay, so that checks out, yeah? So that input corresponds to that context. And so now the reasoning is the same as before. These 3 observables for which we get individually random outcomes, these observables multiply to that observable, which has a definite value of -1. And eigenvalue -1 in terms of the s's means s equals 1. When I add up modulo 2, these 3 s values, individually random, I am guaranteed for this parity to get the value of 1, corresponding to eigenvalue -1. Okay, so that's going to happen in this context. So if my input is such, then the corresponding output is 1. Okay, and so now finally, without going through it in detail, so the other 2 outputs, 0, 1 is 1, and 1, 0 is also 1, and that corresponds to the ones that we haven't touched yet, here, here, and there. Yeah? Okay, and now we have the Boolean table all together. Yeah, so we have 4 input combinations, 4 outputs. Yeah, and we see that this is the OR gate. So our output O is, yeah, I1 or I2. Okay, good. So that's the proof for the OR gate, the nonlinear Boolean function combination based on Mermin's star. So that's the thing. So that was just an individual example. And so Anders and Brown, what they did, they took this contextuality proof and turned it into a little measurement-based quantum computer. So, and the question that now arises is, how does this generalize? Is this connection between contextuality and measurement-based quantum computation more general than this? Is there a general connection, or is it just tied to specific examples? Yeah, and that's the remaining thing for us to discuss. And now comes the general. So yeah, we have seen the connection in an example, and so the question is it general, or is it just tied to a couple of examples? And it is general. So we have 2 theorems about it. So we have a first theorem, and let's begin with the first theorem. So, and that generalizes the discussion that we witnessed in the Anders and Brown scenario, in the Greenberger-Horn-Zeilinger state, which had the OR in this case was deterministically computed. So let's talk about deterministic computation, and the result is every measurement-based quantum computation of this kind, L2, linear mod 2 classical site processing, which deterministically evaluates a nonlinear Boolean function, is contextual. Okay, so that's, so the example we saw generalized in this way. And so now that we have this theorem, we wonder, then we just begin to criticize it and think, it's maybe not the theorem we want, because it says deterministic, deterministic function evaluation. And so likely you would say, oh, that's too constraining. I mean, mostly stuff in the quantum world is probabilistic. So you would want to relax this condition from deterministic to probabilistic function evaluation with sufficiently high success probability. Yeah? But you need to have this theorem first before you can criticize what it is lacking. But now that we have it, and we will prove it shortly, so we will address this aspect of deterministic versus probabilistic function evaluation. Okay, and so we have theorem 2, which is basically the same, except this is gone. So now we have a function as before, and it is evaluated now only probabilistically. And so what this means, so we have an average success probability, and this means averaged over all input values. The average success probability is above a certain threshold, and I come to talk about what this thing is. So if you are above this probability threshold, then you are contextual. If you are below it, you can't tell, but if you are above this threshold, then you sure must be contextual. Okay, so now let's parse this. Let's parse this expression here. So what we have here, so this is functions from m bits to 1 in this case, and you see the m here in this expression. So 2 to the m is a number of input values you can have. So that's why it appears here. And what is up in the numerator is the Hamming distance from the closest linear function. Okay, so what the Hamming distance is, and let's just quickly do this for the OR gate on the board. Yeah, so we have a table here. So this is the OR. Okay, so we have 4 possible inputs. So the OR evaluates to 0, 1, 1, 1. And now we have some other function, say and, just as an example. And is not going to be super interesting for us today, and so the and is 0, 0, 0, 1. So so what am I doing here? I want to illustrate the notion of Hamming distance. So Hamming distance counts the positions where the two functions differ. So, and here's the same, no contribution to the Hamming distance. Here they differ, contribution. Here they differ, contribution. Here they differ, no contribution. So the Hamming distance between the OR and the AND is 2. So that's what it is. Okay, and now, so what we really care about here in this expression is the Hamming distance of the function O, whatever it is, and a function on m bits to the closest linear function. So the end is not a linear function. So we look at all the linear functions there are and then pick the one that is the closest to this function O by Hamming distance. Yeah. So that, for every function here, this thing will have a value somewhere between 0 and 2 to the m minus 1. Yeah, okay, so now we have roughly an idea for what this expression is. And so this gives us the thresholds for contextuality. Good. Okay, and so why are we going for this more complicated thing? Because we wanted to go beyond deterministic computations. Yeah, and this is what we get. So we get a success probability threshold now, and that depends on the function that is being computed. Okay, so the theorem number 2, this is the core theorem of today, and the remainder of this class is about proving it. Okay, and a bunch of limiting cases and discussion and so forth. Okay, but before I move on, yeah, so this is the remainder of this lecture is about establishing this essentially. So I hope that at least the statement is clear. Yes?
The Hamming distance completely independent from m, because like imagining two functions that have like where m is low, then differing in some inputs is more crucial than if m is very large.
Yes. So yeah, so depending on m, yeah, the range for the Hamming distance differs. The larger m, yeah, so I mean, the more places to check, and the larger the Hamming distance can be. Yeah, so the maximum value for the Hamming distance between any pair of functions is 2 to the m. Yeah, so that you just take some function and the function value is negated, so you differ in every spot. Then the Hamming distance is 2 to the m. So that's the largest it can possibly take. Yeah, and so the m matters for gauging what low or small or large Hamming distance means. And here in this formula, so this fact, this numerator. Denominator rather, this denominator takes care of this dependence. Yeah, so this number here is always between 0 and 1/2. Not the case? Okay, then let's see. So the theorem. Good. Okay, so let's just go back to the example. So we want to connect our general statements to what we said before. I mean, the theorems that we now have should cover this example. So let's see if that checks out. Yeah? So theorem 1 said, every such measurement-based quantum computation which deterministically evaluates nonlinear Boolean function is contextual. Okay, so the OR gate is a nonlinear Boolean function, and therefore the theorem says, yeah, this computation is contextual, which we already knew. We had discussed the example before, but it is consistent with the theorem. Theorem 2. Okay, so of the, so now let's see. So this gives us now a probability threshold beyond, for the success probability of function evaluation, beyond which we are contextual. So let's compute what this thing is. Okay, so closest linear function to the OR. What comes to mind? Identity? Like what? So the identity, all ones. Yeah, I think that does it. So a constant function, so Hamming distance is 1. Yeah? Okay, so this is by example, and yes, constant function is a linear function, so it applies. Hamming distance cannot be smaller than 1 because then it would need to be 0, but that can't be because it's a nonlinear function. So Hamming distance is indeed 1. So we plug it in here. So this is 1 minus 1 over 4. So 3/4. Yeah. So the success probability, the critical success probability is 3/4. And if we are above in evaluating that OR gate, then this means the setting is contextual, cannot be described by non-contextual hidden variable. So this is what the two theorems say about the scenario we already knew. Okay, so now come the proofs. And we do the proof basically 3 times over, and it's becoming successively more complicated. So we begin with the proof of the first theorem, where the computation is deterministic. I mean, it's very similar arguments, but progressively slightly more complicated. Okay, and so we don't go at, the thing right away. We first prove a simpler case where there's no temporal order. So let me remind you, we had this vector of choices for measurement basis. It was of this form, something like this. Yeah? And now we say that this isn't there. The matrix T is 0. There's no adaptivity of measurement bases. So the Anderson-Brown example we just saw is of that kind. Yeah? So the measurement basis only depended on the input. There was no temporal dependence. So let's look at that scenario first. It is slightly simpler. Okay, good. So the overall outline is that we show that if this thing is not contextual, that is, if a hidden variable model exists for all the potentially measurable observables, then the function computed is mod 2 linear in the input. And so then our result is the contrapositive of that. Okay, good. So now sorry for this bunch of text here, but maybe we can actually go through it. Okay, so if this thing is not contextual, then we have all these value assignments. Yeah? And so there is, for every location, physical location, there is now an outcome, sk, as a function of this choice of basis qk. We can draw a diagram. And so with values 0 and 1, so on this axis we have qk, and on this axis we have sk. Yeah, and so there is, and so there's a value here for q equals 0, let's say sk is 1, and we have another value for qk equals 1, and let's just say, as for an example, that value is 0. And so now I observe, it's kind of, there is really nothing in between, but I observe that if I have only two function values to match, I can always do this with a linear function. Yeah? And so that is this relation. Yeah? So sk is some number ck plus some tilde dk times qk. So qk is the choice of measurement basis 0, 1. So in this example that I've shown here, ck would be 1 and dk would also be 1. Yeah? Okay. So the reason that I can write this down in this simple fashion is that by assumption I have only two choices of measurement basis per site, and 2 points I can always fit with a linear function. Yeah, so that is the special situation here. So this holds. Yeah? And we need to keep in mind that this object sk comes first, or the collection of these measurement outcomes. So these numbers here, c and d, they depend on the chosen value assignment. So it may be good to keep in mind. Okay, so maybe I let that settle for a moment. Okay, so we can write this in a matrix form. Yeah, so this is what you see up here. So this is now for all measurement outcomes that really occur in the measurement. Yeah, and we can write this as some constant vector plus a matrix times q, and D is a diagonal matrix with all these entries, and C is just a column vector with all the entries C that we had. Okay, so this is a relation. This is just a way of writing our value assignment. Okay, and now we combine this with one of the linear processing relations. So we had choice of measurement basis is given by Q, some matrix times the input. Okay, so we are inserting, let me just, I need to figure out what we are inserting where. I think we are inserting this into this up here. Okay, so we have, at this point, we have all our equations together. We just kind of need to combine them properly. Yeah, so we take this thing, yeah, Q is here, expressed like so, and we plug this in over here. So then we are getting this result. So the measurement outcomes that occur are now some constant vector plus something linear in the input. And finally, we have this relation, final processing relation between output and measurement outcomes. It's also linear mod 2. And now we take this thing and plug it in here. And so then we get another linear relation. Yeah, we're just inserting linear relations into linear relations. And so the outcome of that, so then we find that the output, given the value assignment S that we started with, is constant plus input vector times matrix, where the constant is given in a certain form and that matrix is given in a certain form. And we don't care what they are. All that matters is that this output is a linear function of the input. Good. And that is now for a particular value assignment. So all these matrices and constants, they came from that particular value assignment. Okay, and so now maybe we have a probabilistic mixture of these value assignments, but the computation is deterministic, so they need to all, even if S differs, they all need to lead to the same output as a function of input. And yeah, so okay, but it's a linear function, so that's the main thing. So from the assumption of having a value assignment, we get to a linear function. And so that was kind of the first iteration of the proof. It was under the assumption that we are being deterministic and that we have no temporal order, matrix T equals 0. But this is the basic way this proof operates. And if you digested that, then we will next remove the assumption of determinism. Oh, excuse me, no. Next thing we will do is we will remove the assumption of no temporal order. So that's the next thing that's going to happen. So and it begins completely the same. Yeah. So you've seen this line before. Yeah. This is that. Yeah. So again, the values that occur in the value assignment, they can be parameterized in this linear fashion in terms of the choices of measurement basis. This is just the fact that, we only need to match 2 points and can do this with a linear function. Good. And now we just operate with these, we operate, so we're getting the same equation. You've seen this before. It's what we had before, but now in vector form rather than component-wise. And now, we wanna operate with this and with the linear processing relation for the adaptation of measurement basis. Exactly what we did last time, except now that the relation is more complicated because this term no longer vanishes. Yeah, so we're now in the general temporally ordered case. So in general, this matrix doesn't vanish. Okay, and so so that is now our situation. And so we need to be a little bit more clever and it's a little bit more elaborate. But we are working with the very same pair of linear equations. So what we now do in this case, we are plugging this relation in here. So maybe let me do this on the board so that we can sort the terms. Have more time to sort the terms. Yeah, so, okay. So we are plugging, what did I say? We are plugging the equation on the upper left in the classical side processing relation for the choice of measurement basis. So we are getting Q is TS, but TS is TC plus TDQ. Just you see, inserted. And then we have this leftover term Qi, Q times input vector I, and this is all modulo 2. So, okay, so now we have, so last time, if I was not last time, what did we solve for? Let me just try to go back. yeah, we wanted to solve for S. Okay, so, excuse me. Yeah, sorry, I did it wrong. Let me, I did it the wrong way around. We want an equation for S and we want to eliminate Q. Okay, so we take this relation and put it in there. So we get S of Q, or S simply is C plus dq, and q is this. So this is dts plus dqi. Is that right? Yeah. Yeah. I think this is it. Can somebody following? I think this is right. So I need another piece of chalk and I need to speed up. Okay, and so now we see we have S on the left and the right. Okay, so we bring this term to the left, and this is addition modulo 2, so -1 is +1. And so we have identity plus dt times, so these are all matrices, times vector S is C plus dqi. Okay, fantastic. So I'm in accordance with what's on the board. Okay, so this is how this thing comes about. Okay, and so all I need to do is to invert this matrix. And so the question arises, is this thing invertible at all? We see, and so remember this talk about lower triangularity, yeah? So this matrix, and that has the physical reason for that is temporal order. So this is lower triangular. So it has 0 on the diagonal, 0 above, and then some stuff here, zeros and ones. D, if you remember, was diagonal. And so it doesn't affect the structure. So multiplying with the diagonal matrix leaves this lower triagonal with nothing on the diagonal. And now we are adding the identity. And so this means the whole thing has identity on the diagonal, ones on the diagonal, and then stuff below. And that is an invertible matrix. Yeah? So you can immediately check that the rows of it are linearly independent. So that matrix can be inverted, and so you invert it, and you get, after inversion, you get S as a function, as a linear function of some constant and linear in the input I. So the linear on the input I, this doesn't go away. Yeah, then so that was for the measurement record, and now you plug this into this further linear relation, and yeah, you get this. So it's completely what we had before with different matrices and constants, but the upshot is, well, the result is still the same. The function, starting from the assumption of a hidden variable model value assignment, the function of output, of input is linear. Linear function. Same result, hasn't changed. Yeah, then the remainder of the argument is the same we had before. Okay, I think it is. Okay, so that is the full proof of theorem 1. And yeah, so this mumbo jumbo dealing with this matrix, arguing that this is invertible, this is the key step. So now the theorem 2, which is the theorem that really interests us, this is kind of very little work now. Yeah, so not much left to do, even though the result is quite a bit stronger. Good. So yeah, so as far as I am concerned, we can move on to the proof of theorem 2. Is that fine? Yeah? Good. Okay. So proof of theorem 2. So just as a reminder of what it says, so now we have a threshold and success probability, and if we exceed that threshold, we are for sure content. This is what we learned in the proof of theorem 1, and we are going to use this. So for any value assignment S that we start with, yeah, 2 values per location, 2 observables per location, but whatever the based on this hidden variable model, the output function is linear in the input. You know, this was the proof of theorem 1. Okay, and so that's what we are going to use now. And so we are inching forward in a bunch of steps. So the next question that we ask ourselves is, so for how many input values does this predicted function fail to reproduce the intended function? So this is what the hidden variable model does. This is what we want to compute. So in how many locations do we fail to predict? Yeah, and that's precisely given here by our notion of Hamming distance. Yeah, so the number of locations where we fail in, by definition of Hamming distance, is the Hamming distance between the intended function and the function that the hidden variable model predicts based on a value assignment S. Okay, so this is, so just a definition, basically, of the Hamming distance. And so we ask ourselves the next question, so if the input is completely randomly chosen based on having a value assignment S, what is the probability of failure for computing the output? Yeah? And so we fail in this many locations out of 2 to the m. And if the input values are chosen randomly, then the conditional probability of failure, if we are in this particular hidden variable model value assignment, is this Hamming distance divided by 2 to the m. Okay, so that's just what it is. And now we have a bound on that number. And so since, as we proved before, this function is a linear function, so then this Hamming distance is larger than the Hamming distance from the set of all linear functions. Yeah? So this might be the closest linear function, it might not be. So that Hamming distance is always larger or equal to the Hamming distance from the closest linear function. Now I'm combining these two things, and I find that the probability of failure given a particular value assignment is larger or equal to this ratio. And if I compare now this with that, I have lost something and gained something. So what I have lost is the equality sign. It's replaced by a bound, so it's a weaker thing. But what we have gained comparing this and that is the dependence on the particular function predicted by the value assignment. Yeah, so we have now a general expression that holds holds independent of what that value assignment is. And that's a gain, as we will see shortly. Yeah, okay. And so now let's assume the hidden variable model exists and we have some probability function over the various value assignments, and then the overall probability of failure is the sum over all value assignments of probability of a given value assignment times conditional probability of failure given that value assignment. Yeah, so it's just Bayes' rule of probability. Okay, and so then we bound it by this, so making it independent of the particular OS here, and then we see the bound doesn't depend on S anymore, so we take that out, and the sum of the probabilities is just 1. Okay, so the failure probability is larger or equal to this. Okay, so to summarize, if a hidden variable model exists, probability of failure is larger or equal to this, means the success probability is smaller or equal to the complement. Yeah? And now we take the contrapositive of that statement. So if the success probability is larger than this, then a hidden variable model does not exist. End of proof. Okay, so that's it. Let me just, so you will see it in the slides. So there's two consequences here. I have only time for one, and not even that. So you want to know in the theorem, how low can the success probability, the threshold success probability be? Yeah, it's definitely, we see this in the expression, it depends on the Boolean function we think about. And there is something that coding theorists, for some reason, have an interest in studying. It's called the bend functions. And these are the farthest away in Hamming distance from any linear Boolean functions. For some reason, coding theorists in the 1970s had an interest in studying that. Who knows why? But at any rate, the bend functions are the functions that are the largest distance away from linear Boolean functions, and it is known what that Hamming distance is. So this is a maximal, 2 to the m would be the maximal Hamming distance between two m-bit Boolean functions. So that distance here to the closest linear function is 1/2 of maximal, so 2 to the m minus 1, minus a exponential correction term that has m over 2 in the exponent, essentially, rather than m. Okay, and if you plug this into the theorem, then you find that for bend functions, the success probability must be larger than 1/2 and a tiny little bit to be contextual. So you can be almost completely random and still be contextual. So if you are perfectly random, then you're not, but if you are a tiny bit above complete randomness, then you're already contextual for the bend. Yeah, good. Okay, so that's all for today.